We are continuing our discussion about confidence intervals, and let's focus here on confidence intervals for means. So we want to make a statement that the probability of mu is between two values here. So we have a lower bound and an upper bound, and it equals a certain level of confidence. So maybe that's 95%, 90%, or 99%. Those are the most common levels of confidence. Now, if you're doing a confidence interval, so you're trying to find these upper and lower bounds, there are some assumptions we are making. We are assuming that we have a random sample. So it is a probability sampling method. We are pulling information at random from the greater population, which means it's going to represent some of the variability that exists within the population. The other assumption we are making is that the population is normally distributed, or that the population is not normal and the sample size is large enough that we can use that approximation. And so this is that central limit theorem that we talked about in previous videos. We need this assumption here for our confidence intervals in order to use that standard normal distribution. The other thing we're assuming, at least right now, is that the variance or standard deviation of the population is known so that we know sigma. We will talk about in just a moment what if you don't know the level of variability in the population, because in reality you probably don't. And then we're going to use not the standard normal distribution, but we'll use something called student's t. So we'll waive this assumption in just a moment. But let's start here where we have a random sample, our population, our underlying population that we're gathering information from is normally distributed, or the sample size is large enough we can assume a normal distribution. So this would be like if we are trying to estimate what is the average age of people in Alberta. If that data of ages, so the underlying population, is normally distributed so that their mean, median, and mode are the same, and then we have an equal number of extremes on one end and the other, then we can do this. We can look at creating a confidence interval for the average age of Alberta from our sample statistic, the average age of our sample. If the population is not normally distributed, then we need a big enough sample size so that we can take into consideration that there isn't just this central tendency with the ages of people in Alberta, but maybe it's skewed one direction or another. Maybe there's lots of young people, maybe there's lots of old people. And so we need a big enough sample size that's going to represent the fact that there is this extra amount of people in one of these extremes. All right, let's look at how this works. A 95% confidence interval. Using our central limit theorem, we can take our sampling distribution and we can say the center of the sampling distribution, the average of the averages, is the population mean. And we can find the z-score. So remember, when we deal with x bar minus mu divided by sigma over the square root of n. Okay, and actually we'll just go back up. This is the formula you've seen before. Right? So central limit theorem lets us use this z-score in order to create our confidence interval. So if we are going to convert our data into a z-score and we want, let's say, a 95% confidence interval, we need to know what this z-score is that goes with a 95% confidence interval. Okay. And we did look at that briefly in our previous video. We talked about how with a 95% confidence interval, the z-score is 1.96. And we talked about how we know that because if we go to 1.96, which is the one I circled right here, you get 97.5, which means that everything to the left of this 1.96 is 97.5, which leaves 0.025 on this right tail. Well, if we want a confidence interval, we want to go between 1.96 and negative 1.96. We want the same size tails on each side, and so that takes that 97.5% minus that 2.5%, which gives us the 95% confidence interval. Okay. So when we're looking at our confidence interval, what we're saying is the probability that our negative z, alpha divided by 2, is between our x bar minus mu sigma over the square root of n is less than z alpha divided by 2. And we're doing that with a probability of 95%. So this negative z alpha over 2 is that negative 1.96. We find our x bar minus mu sigma over n, square root of n, and 1.96, all equal to 95%. Well, what we're doing here is we're going to essentially take this formula and rearrange it so that ultimately, do I have this written somewhere? Hang on. There we go. Okay. So that ultimately we've rearranged the formula so that we're just looking for what is mu. And so that's going to give us this lower bound here where it is our average minus our value of z, which in this case is 1.96. X bar plus 1.96 on this end, so we get those two extremes, and then sigma divided by the square root of n. In this particular confidence interval, remember we said that we know the standard deviation of the population. So we're able to use this formula with this sigma in it because we assume we already know something about the population of interest. And 1 minus alpha in this case is 95%. Which means that we are willing to accept an error of 5%. Okay, so let's just backtrack a little bit here because I'm getting ahead of myself. So the area under the curve between the two cutoffs, that's going to be equal to the area under the curve between our two cutoffs here is going to be equal to that 95% confidence interval. That's this 95% here. And if we're doing what we call a two-tailed test or a confidence interval, then the tails are going to be equal in amount. So 1 minus alpha is our 95%, which means alpha divided by 2 is that 0.025 on each side. So we're accepting an error of 5%. Half of that error can be because it's too big, and half can be because it is too small. So in this case, we have that 95% in the center. Well, what do we use for these z's if we are doing a different confidence level? So we've been looking at a 95% confidence level, in which case we're using a z of alpha over 2 equal to 1.96. And you do the negative version on one side and the positive version on the other. Okay, for your 95% confidence interval. But what about for a 99% confidence interval? What about for a 90%? We've technically already done the 99% confidence interval. We did that in a previous video. I'll just do it again here. I don't know where I went. None of this. Lost my place. Lost my mind. Went the wrong way. Okay, so 99%, which means with a 99% confidence interval, alpha equals 1%. Alpha divided by 2 equals half of that. So that's going to be half of a percent, or 0.005. Okay, so what do we do with that? Well, if we go to our standard normal table, remember the tables show you everything to the left of the z-score. And if we want to have one where, I don't know what's wrong with this particular tab. It does not want me to write on it. But if we have where on the wing we are leaving, if we just go back here, remember it's going to be 0.005. So if you want 0.005 out here on the wing, then what does the rest have to be? The rest has to be 0.995. I apologize, it's being buggy here. So we're looking for the number on the inside here that is 0.995. And in fact, you'll recall, and you can't see it because my face is covering it, but we found this previously, 0.99506. That leaves 0.005 in the wing, and that goes with 2.5. I'm going to move my face back down. It goes with 2.58. So Z alpha divided by 2 for a 99% confidence interval is going to be 2.58. Okay, what about a 90% confidence interval? So if we want a 90% confidence interval, there's 90% here in the middle. That means that alpha is 1 minus 90%, so that's 10%. And that means alpha divided by 2 is 5%. Well, if you're looking that up on the table, you're looking for, here is 0.05, and that means the rest of this is going to be 0.95. Okay, so let's go to our table, find 0.95. Closest number to 0.95. And we get here, okay. So often what people use for this is 1.64. Okay, this one here being the closest to 0.95. So let's just go here. Come on, come back. Oh no, I've just lost my mind. 1.64. So 1.64, 1.96, 2.58 are what the Zs you will be using for your 90, 95, and 99% confidence intervals. So it's a good idea just to remember those. 1.64, 1.96, 2.58. All right, so constructing a confidence interval. What we would do then is where you see the Z, that's where we put in the 1.96 if it's a 95% confidence interval. And then we simply place in our X bar, our sigma, and the square root of n to find the upper and lower values. So let us do that. Did I do that? We'll do that in just a second. Okay, first, one more thing before we do that. When we do a confidence interval for a mean, we essentially have two parts to the upper and lower bound. The two parts to the upper and lower bound, we have the point estimate, that's the X bar here, and then the other piece where we have our sigma divided by square root of n times Z, where it's alpha divided by 2, that is what is called the margin of error. So our confidence intervals are made up of two parts, a point estimate, and then we subtract that margin of error to get the lower bound, and we add the margin of error to get the upper bound. So just a note that the width of the confidence interval is going to be impacted by three things. The sample size. The larger the sample size, what that's going to do is divide by a bigger and bigger number, shrinking the margin of error. So remember, if your sample is your population, so you have a census, then your sample statistic is your population parameter. There is no margin of error. Your point estimate is spot on. And, well, we don't have that. We don't have a census, but we have bigger and bigger sample sizes. The bigger the sample size, the bigger this n, which if we divide by a bigger and bigger number, the margin of error gets tiny, and we just get to that point estimate. So your confidence interval gets narrow, the bigger your sample size. The more variability in the population, the wider your confidence interval gets, because this sigma represents how much variation there is in the population data. And so then we're going to need a wider interval to estimate that population parameter, because we have so many differences within that population that we have to take into consideration. Okay. Then the last one is the confidence level, 90%, 95%, 99%. That's changing the Z here. And you'll notice, where do we go? That the more confident you want to be, the higher the Z, and that means that it's going to make your confidence interval wider. The more accurate you want to be, the wider the interval. Okay? And we talked about before how we could have a super wide interval, but then is that actually useful for making decisions if the actual number can be anywhere within a big long range? So you want it to be narrow enough to make a decision, to be able to use the information, but we also want to be accurate. And so one of the ways that we can deal with that is a bigger sample size allows for the narrower confidence interval, while at the same time allowing for the same or higher accuracy. Okay, so an example. All right, we're back to our battery manufacturing. So we wish to investigate the length of time a battery will last between charges at a fixed load. We have a sample of 12 batteries. We have a mean length of time of 4.3. So X bar is 4.3, N is 12, and the standard deviation of battery life in the population is known. It is 0.3. That allows us to use sigma in our Z. So construct a 95% confidence interval for the population mean. So remember, the lower bound is X bar, that's the point estimate, minus Z alpha divided by 2 times sigma over the square root of N. And then mu is going to be in between that. And then we have X bar plus Z alpha divided by 2 times sigma over the square root of N. And it's 95%. The part you can't see that I just wrote underneath my face is that 95%. Okay. Okay, let's do this. So we have 4.3 is the average. We need our Z for 95% confidence. Remember, it's alpha over 2, so we're putting that alpha of 0.05, that's the amount of error we're willing to accept, and we're dividing that to be on either side. So we're going to need a Z, 95% of 1.96 minus 1.96 times sigma here is 0.3 divided by the square root of 12. Okay. So if I'm going to pull up some Excel, and let's change this so we can see all this at the same time. Let's go this way. Okay, so doing this by hand, we can do 4.3 minus, and we have 1.96 times, let's just space this out. Here we go. Okay, let's do first order of operations. So anything, let's do first easiest, square root of 12. And you got to have the right command, square root of 12. Okay, then we're going to do equals 0.3 divided by that square root of 12. That gives us the part that is in the parentheses. Then what we're going to do is we're going to multiply that times our 1.96. All right, so our margin of error is 0.1697. Can you see that? This might be too tiny here. Okay, so what I did is I took the square root of 12, I did 0.3 divided by the square root of 12, and then I did times 1.96, which gives me this margin of error here. And the reason to do that separately is that we can then do 4.3 minus this, gives us the lower bound, and we can do 4.3 plus that, gives us, whoops, the wrong one, the upper bound. Okay. So what are we concluding then? We are 95% confident that the population mean, this being the mean length of time that the battery lasts, is between, and of course I lost my Excel. Where'd it go? Is between 4.13 hours and 4.47 hours. Okay. So, questions. Is it reasonable to claim that the battery will last 4.25 hours? Well, is it reasonable? Is that within that list that we just looked at. So let me just move this up here. So 4.25 falls within that, so it's reasonable to claim the batteries will last 4.25 hours. The underlying population parameter, the mean length of time, mu, could be 4.25. It's in between the two. Is it reasonable to claim the batteries will last 5 hours? Well, no, because with 95% confidence, 5 hours is not within that range at all. Now, we can do this, so we did all this by hand, but you can also do this in Excel. So we're doing confidence norm. And when you do confidence norm, you provide 3 pieces of information: alpha, standard deviation, and size. See if I can remember how to do this. Our standard deviation was, what was that number? 0.3. And our sample size was 12. Okay, so notice here this confidence.norm gives us that same margin of error. So if you have your X bar 4.3, you can use confidence.norm, give it the alpha. You don't have to do alpha divided by 2, just do alpha, it'll split it. Give it the standard deviation for the population, and give it your sample size, and it will count your margin of error for you, in which case then the last step is just to subtract the margin of error from your point estimate and to add the margin of error to your point estimate. Okay, so there we get our confidence interval for our mean.